In this video, we're going to talk about radicals and rational exponents. And to start off, let's talk about what a radical is. A radical, or another word for saying radical, is root, which is the inverse operation of raising something to a power. So, for example, if I ask you to take 5 and square it, or raise it to the second power, that gives me 25. But if I wanted to take the square root of 25, it does the inverse and gives me back the base. The symbol of the square root is called the radical, and that could be a third root, a fourth root, it can be any kind of root, and the symbol is the radical. What's underneath the radical is called the radicand, and the whole expression together, this whole thing here, the square root of 25, is called the radical expression. There is a difference between even roots and odd roots. If I ask you to take the square root of 25, I would say that that is 5, because 5 squared is 25. If I asked you to find the square root of negative 25, this does not exist because there is no number that when I square it, I would get negative 25. I can't square negative 5 and get negative 25 because a negative 5 times a negative 5, that would be a negative times a negative, would give me a positive number. That would be impossible. And of course, if I take 5 squared, 5 times 5, that would definitely not give me negative 25. So the difference between an even and an odd root is that I cannot have a negative number under an even root and have it be a real number. However, I can take an odd root of a negative number. For example, I could take the cubed root of negative 8 and say that that's equal to negative 2, because negative 2 to the third power is negative 8. Negative 2 times negative 2 times negative 2 is negative 8. That does exist. So what it comes down to is, just remember that when you're looking at an even root, a root that is the square root, or the fourth root, or the sixth root, or something like that, you cannot take the negative number of an even root because it doesn't exist within the set of real numbers. But you can take an odd root of a negative number. That is possible. Now, if I asked you the difference between the square root written with the symbol or the word square root, this symbol here indicates that it's automatically a positive number. It's not written in there, but we assume that that's a positive square root. So if I asked you in words, find the square root of 100, that means what could I square to get 100? Well, there are two possibilities. Positive 10 squared would give me 100, but also negative 10 squared would give me 100. So if I ask you to tell me what the square root of 100 is, you would say plus or minus 10. There's two possible answers. However, if I wrote the symbol like this, I'm automatically assuming that I'm talking about the positive value of that. So my only answer for that would be positive 10. So there is a difference between writing it as a symbol as a positive square root versus asking you to write it in words. This example in part B, when we evaluate square roots, this is the square root of a square root. When we talked about order of operations, remember, if you have grouping symbols, you want to make sure that you do the innermost first. So this would be the square root of 4, because I'm rewriting the square root of 16 as 4. And then I take the square root of 4, and I would get 2. When I evaluate this square root, you always want to do what's inside your grouping symbols first. And this square root is grouping the 25 and the 144 together. So I would take 144 plus 25 and add those first. That would give me 169. And when I take the square root of 169, that is 13. It is 13 because 13 squared is 169. Remember, when I'm asking you for a positive square root, it's asking what could I square to get that number that's underneath the square root symbol. For example D, I'm asking for you to take the square root of 49 and then subtract the square root of 81. The square root of 49 is 7 because 7 squared would give me 49. And then I'm going to subtract the square root of 81. The square root of 81 is 9 because 9 squared is 81. And then when I take 7 minus 9 to finish evaluating this expression, I would get negative 2. When you want to simplify a radical, you can make a factor tree and break this down. I'm going to take 196 and I'm going to break this down and create my factor tree. 196 is 2 times 98, and then 98 can be broken down into 2 times 49, and then 49 can be broken down into 7 times 7. So 196 can be written as 2 times 2 times 7 times 7. Because this is the square root, that means anytime I have a pair of the same number underneath that root, I can pull it on the outside of the root as one of those numbers. The same reason why the square root of 4 is 2, that's because I can write 4 as 2 times 2, and because I have a pair of 2's under there, I can get rid of the radical and pull it out as 1, 2. So, because I have 2 2's under there, I can take that out as 1, 2. And because I have 2 7's under there, I can take those 2 7's out and bring it outside the radical as a 7. So my answer is going to be 14. Here's an example where it doesn't work out even. 32, we're going to break it down into our factor tree. 32 can be written as 2 times 16. And then 16 can still break down into 2 times 8. 8 can be broken down into 2 times 4. And 4 can be broken down into 2 times 2. So I have 1, 2, 3, 4, 5 2's. So I can rewrite 32 as 2 times 2 times 2 times 2 times 2 as 5 2's. Now every time I have 2 of the same number under there, I can bring it outside of the radical, because this is a square root, I can bring it outside of the radical as one of those numbers. So there's a pair of 2's, I can bring it outside as 1, 2. Here's another pair of 2's, I can bring it outside as another 2. This 2 doesn't have a partner, so it's going to stay underneath the radical. So my final answer is going to be 2 times 2 on the outside, which is 4, and I still have 1 2 left underneath. Now with the cubed root, that means you're looking for 3 things to group together before you can bring it outside of the radical as one of those numbers. So we're going to break down 250 into 2 times 125, and then 125 can be broken down into 5 times 25, and then 25 can be broken down into 5 times 5. So my factor tree, I have 250 is equal to 2 times 5 times 5 times 5. So I'm going to rewrite the cubed root of 250 as the cubed root of 2 times 5 times 5 times 5. So every time I have 3 of the same number underneath the radical, I can bring it out as 1 because this is the cubed root. So I have 3 5's under there, so I can bring it out as 1 5. So I have 5, and then the cubed root of 2 left over. That 2 cannot come out from underneath the radical because it doesn't have 2 other 2's with it to pull it out as a group of 3. Now we have a 4th root. So that means I need to have something in a group of 4 in order to pull it out as one of those numbers on the outside of the radical. In a previous example, we found that 32 was 2 times 2 times 2 times 2 times 2. Then we have 5 x's, 1, 2, 3, 4, 5. Then we have 8 y's, and 3 z's. Because this is the 4th root, every single time I see 4 of the same item, I can bring it outside as one of those items. So I have here a group of 4 2's. So I can take that on the outside as 1 2. I have 4 x's here. So I can take that outside as 1 x. I have 4 y's here, and then I have another 4 y's here. So I have one group of 4 y's and then another group of 4 y's. So I have 2 y's on the outside. And then these z's at the end, I don't have a 4th z to group it together to pull it out as a group of 4. So I have to keep those 3 z's underneath the radical. So what is left is 2. I have a 2 left under there. I have 1 x left under there. And I have 3 z's left under there. That's what's left. And so when I finish cleaning this up, on the outside of the radical, what we pulled out was 2xy squared, because I have the y times the y. And then what's left under the radical, I still have the 4th root of 2xz to the 3rd. Now, I wrote out all those x's and all the y's and all the 2's and all the z's so that you can see the process in which I go through. But there is a shortcut, and you don't need to do that every time. What you can do to look at the shortcut, you look at your root. It's a root of 4. So instead of writing out all 5 x's, you can say 4 goes into 5 one time evenly, so I can pull out 1 x, and I have a remainder of 1. So I still have 1 x left underneath the radical. 4 goes into 8 an even number of times, 2 times. So I have 2 groups of 4. So I'm going to pull out a y squared. And that is a remainder of 0. So I should have no more y's left underneath the radical. 4 can't go into 3. So I leave all 3 z's underneath the radical. So you want to see how many times that root goes into your exponent, and whatever's left over has to stay underneath your radical. Example E is the cubed root of 8, a to the 4th, b to the 7th. So now let's use our shortcut that I just showed you. The cubed root of 8, we should know what that is. That's 2, because 2 times 2 times 2 is 8. So that can come outside the radical. Now, I have 4 a's under the radical. 3 goes into 4 one time even, but I still have 1 left over, so I have an a left over underneath. 3 goes into 7 2 times for the b to the 7th. That 3 goes into the 7th power twice even, so I have b squared on the outside, but I still have 1b left over underneath. So here is my final answer using the shortcut. Okay, now when we want to multiply radicals, in order to multiply radicals, we have to make sure that they are the same root. In other words, I cannot multiply what's underneath the radicals together if I have a square root and a cubed root. The roots have to be the same in order to multiply what's underneath them together. So in this case, since they're both the square root, I can just multiply what's underneath them together, and rewrite it as the square root of 140. And then from there we can simplify it. So 140 can be written as 2 times 70. 70 can be written as 2 times 35. And 35 can be written as 5 times 7. So my factorization for 140 is 2 times 2 times 5 times 7. So because this is the square root, I'm looking for numbers that are the same in groups of 2. Since I have 2 2's under here, I can pull those 2 2's out as 1 2. And I'm still left with a 5 and a 7 underneath because I don't have 2 5's or 2 7's under there. So when I take the square root of 140, it can simplify as 2 square roots of 35 because I still have the 5 times the 7 left under. In example B, all of those are the same root. They're all cubed roots. So I can just multiply everything together, what's underneath all of their radicals together. So I take 12 times 5, which is 60, and then 60 times 2, which is 120. And then I simplify that. And I break 120 down. 120 is 2 times 60. 60 is 2 times 30. 30 is 2 times 15. And 15 is 3 times 5. So my factorization for 120 is 2 times 2 times 2 times 3 times 5. Because this is the cubed root, I'm looking for numbers that are in groups of 3's. Every time I see a group of 3 of the same number, I can pull it outside the radical as one of those numbers. So I have 3 2's under there, so I can pull out those 3 2's on the outside as 1 2. And what's left is 3 times 5 underneath, which is 15. So my final answer is 2 cubed roots of 15. In example C, again, we have the cubed root of 6 times the cubed root of 20. Since those are both cubed roots, I can multiply what's underneath together. So I'm going to write it as the cubed root, and 6 times 20 is 120. And luckily, since we already figured out the cubed root of 120 in the previous example, we know that it's 2 and then the cubed root of 15. Part D, notice that these have 2 different roots. So I can't use the technique of just multiplying what's underneath together. I can't use that technique. When you want to divide and simplify radical expressions, there are 2 different ways that you can write division with radicals. If it is the same root, in other words, if the numerator and the denominator have the same root, they're both the cubed root or they're both the square root, then you can write the nth root of x over the nth root of y, and that's the same thing as saying the nth root, and you can combine it together as one root of x over y. So you can write it either way as long as it's the same root. So sometimes one way is easier than the other. So for example, in A, I can't take the square root of 200 nicely, and I can't take the square root of 2 nicely. However, because they're both square roots, I can write it together as one square root and write it as 200 over 2, which is the square root of 100, and I know what the square root of 100 is. That's 10. In example B, we're going to look to see if we can do the cubed roots separately, and if we can't, we'll try to combine it into one cubed root and divide. I cannot take the cubed root of negative 81 nicely, but I can take the cubed root of 27 nicely. Since I can't simplify the numerator and the denominator nicely and both of them individually, I'm going to try to combine them and see if that helps make it easier. So I'm going to take the cubed root of negative 81 over 27. Negative 81 divided by 27 is negative 3. Now I can't take the cubed root of negative 3, so I would just leave it as is. The next example, I can take 100 divided by 25, and I can take a to the third divided by a, which is a squared. Using our exponent rules, I know that since I have bases that are the same, a to the third and a have the same bases, I just subtract my exponent. Now I can take the square root of 4, that's 2, and I can take the square root of a squared, that's just a, because I would have a times a, I have two a's, and it can come out as 1a. So just remember, there are two ways that you can simplify radicals when you're dividing. If they are the same root, you can write them individually in the numerator and the denominator, or you can combine them together with the same fraction under one radical. And sometimes one way is easier than the other, so you just try it one way and see if it works, and if it doesn't, you can try it the other way. In order to add and subtract radicals, the radicals need to be the same. So, for example, if I had 3 square roots of 5, and then I had 4 square roots of 5, that means I have a total of 7 square roots of 5. So the square root would stay the same, and I would add the 3 and the 4. Just as if I had 3 x's and I had 4 x's, that would give me a total of 7 x's. So in order to add roots together, they have to be the same. So looking at example A, I have 2 square roots of 10 plus 4 square roots of 40. As it is now, I can't combine them because I can't combine square roots of 10s and square root of 40s together. So I'm going to try to simplify it and see if I can create it so that I have a similar square root. I can't do anything with that square root of 10, but I can simplify that 40 into 2 times 2 times 10. Since this is a square root and I have two 2's under there, I can pull those two 2's on the outside as 1 2. So when I pull this group of 2 on the outside, then it ends up multiplying it by the 4, and I have 4 times 2 on the outside, and I'm left with the square root of 10 on the inside. Now, my square roots are the same, and if I have 2 square roots of 10, and I have 8 square roots of 10, then I have a total of 10 square roots of 10. And now I'm done. In example B, I can't add those cubed roots together as they are right now. I might be able to manipulate this expression when I simplify the cubed root of 128 so that I have a factor of the cubed root of 2. So I'm going to take 128 and I'm going to make my factor tree. 128 can be written as 2 times 64. 64 can be written as 2 times 32. 32 can be written as 2 times 16. 16 can be written as 2 times 8. And 8 can be written as 2 times 2 times 2. So I have 1, 2, 3, 4, 5, 6, 7 2's. So I can rewrite the cubed root of 128 as 7 2's. Because this is the cubed root, I'm looking for groups of 3. Here's a group of 3 2's, and here's another group of 3 2's. So I can bring out, for this group of 2's, I can bring out a 2. Then I can bring a 2 out for this group of 2's, and then I'm still left with this 1 2 underneath. So that I'm left with the cubed root of 2. So on the outside here, I have 4, and then the cubed root of 2, and then I have 2 cubed root of 2. So that gives me a total of 6 cubed root of 2. So here's my final answer. In part C, notice that this is the fourth root of 2, and this is the cubed root of 2. So I can't add these together. This is as simplified as it gets. So I'm going to write down can't simplify any further. Okay, now we're going to talk about rationalizing the denominator. And when we rationalize the denominator, that means we don't want to have any square roots or any roots at all in the denominator. And the method to getting rid of the square root or any root in the denominator is by multiplying the top and the bottom of the fraction by that root. So, by multiplying by the square root of 5 over the square root of 5, like in example A, you're multiplying 1 over the square root of 5 by the quantity 1, so you're not changing the value of 1 over the square root of 5, you're just rearranging it. And when we multiply fractions, we multiply across the top and we multiply across the bottom. So on the top, I have 1 times the square root of 5, which is the square root of 5. And in the denominator, I have the square root of 5 times the square root of 5, which, as you know, when we multiply and the roots are the same, we just multiply what's underneath the roots together. So I have the square root of 25. And then that can simplify as the square root of 5 over 5, because the square root of 25 is just 5. And now we no longer have a square root in the denominator. And in example B, we're going to do the same thing. I'm going to separate the top and the bottom square root. And to get rid of the square root in the denominator, I'm going to multiply the top and the bottom by the square root of 14x. And I can do that because this is equivalent to 1. And when we multiply anything by 1, it doesn't change its value. So all we're doing is we're rearranging this a little bit. So when I take 27 times 14, I get 378, and then I still have x. And then in the denominator, when I take 14 times 14, I get 196 x squared. So in the numerator, I have 378x, and in the denominator, I have 196 x squared. The square root of 196 is 14, and the square root of x squared is just x. So now we have gotten rid of the square root in the denominator. And so what we would need to do now is just simplify the square root in the numerator. So if I take 378 and I break it up into 27 times 14, 27 is 3 times 9, and 9 is 3 times 3. 14 is 7 times 2. So we have the factors 3 times 3 times 3 times 7 times 2, and then I still have x under there. And now, because this is the square root, anytime I have 2 of the same number underneath, I can pull it out as 1. I can pull out these two 3's as a group of 3's and bring it out as 1, 3. So I have a 3 on the outside, and then what's left over inside is 3 times 7 times 2, which is 42x left underneath, all over 14x. And then now we're done. In example C, notice that we have two terms in the denominator now. In example A and B, we had one term in the denominator. So, for example, A, we had just the square root of 5. And in example B, we had just the square root of 14x. But now in the denominator in part C, we have 3 plus the square root of 6. We have more than one term. When that happens and we're trying to rationalize the denominator, we have to do what's called multiplying the top and the bottom by the conjugate. And that's what's going to clear the square root out in that case. In a conjugate, the same exact expression, except for the fact that the operation in the center is going to be opposite. So the conjugate of 3 plus the square root of 6 would be 3 minus the square root of 6. These are conjugates. So what I'm going to do is I'm going to take 1 over 3 plus the square root of 6, and I'm going to multiply the top and the bottom of that fraction by the conjugate of 3 plus the square root of 6, which is 3 minus the square root of 6. when we multiply fractions, we multiply the tops together and the bottoms together. So when I take 1 times 3 minus the square root of 6 in the numerator, that gives me 3 minus the square root of 6. In the denominator, however, we got to remember that we have multiple terms here, so we're going to have to distribute more than once. So I'm going to take 3 times 3, and I'm going to get 9. And then I have to take 3 times negative square root of 6, which is negative 3 square root of 6. I cannot write 3 times the square root of 6 as the square root of 18 because the 3 is on the outside of the square root and the 6 is on the inside. And you can't mix insides and outsides. So you want to make sure if you have something on the outside, it stays on the outside. Then I'm going to take 3 times the square root of 6. That gives me positive 3 square root of 6. And then the last one is the square root of 6 times the square root of 6, which is the square root of 36. Now, when I clean this up, I get 9, and then minus 3 square roots of 6 and positive 3 square roots of 6 add to 0 because one's plus and one's minus, which is the whole point of why we switch the sign in the middle. That's how we're going to get rid of the square root. That is exactly why we do the opposite sign in the center, so that we can get rid of the middle term when we FOIL. Okay, and then the square root of 36 we know is 6. So when I finish this up, I get 3 minus the square root of 6 all over 15. Okay, in example D, we have the same situation where we have 2 terms in the denominator, and when we want to rationalize the denominator that has 2 terms, we need to use the conjugate. So we have 1 plus the square root 11 in the denominator, so we need to multiply the top and the bottom by 1 minus the square root of 11. We're going to multiply fractions. When we multiply fractions, we're going to multiply across the top and across the bottom. So across the top, I have 2 times 1, which is 2. And then I have 2 times minus the square root of 11. So that's going to give me 2 square roots of 11. We do not write that as the square root of 22 because the 2 is on the outside and the 11 is on the inside, and we cannot mix up the insides and the outsides. So the 2 needs to stay on the outside and the 11 needs to stay on the inside. Now, when we multiply the bottom, we have to FOIL because we have multiple terms. So I have to take 1 times 1, and then 1 times minus square root of 11, and then square root of 11 times 1, and then the square root of 11 times the square root of 11 would give me plus the square root of 121. Because the 11s are both under the square root and they're both square roots, I can multiply what's underneath them together, and 11 times 11 is 121. So now on the top I have 2 minus 2 square roots of 11, and in the denominator I can cross off the plus and minus square root of 11, and I'm left with 1 plus the square root of 121. And the square root of 121 is 11. So now I have 2 minus 2 square roots of 11 all over 12. And actually, we can simplify this by taking a 2 out of everything. If I take a 2 out of the 2, that's a 1. If I take a 2 out of the 2 square roots of 11, that leaves me with just square root of 11. And then if I take a 2 out of the 12, that leaves me with 6. So now I have my final answer. Okay, the last topic in this video, we're going to talk about rational exponents, and they are related to radicals and roots. So when I look at a base that has an exponent that is a fraction, that's why it's called rational exponents, because the exponent is a fraction. Remember, rational numbers are any number that can be written as a fraction. This is the same thing as saying a, and then I take the nth root of a to the m. The numerator of the fraction is the exponent for a, but the denominator in a fraction in the exponent is actually a root. So for example, if I gave you 4 to the power of 1/2, that's the same thing as saying 4, and then the numerator of the fraction goes on the inside here. That's the exponent of 4 of the base. And then the denominator is the root. So it's the same thing as saying the square root of 4. So if you put on your calculator 4 to the power of 1/2, you're going to get 2. If I put in on the calculator 8 to the 1/3, that means the third root of 8, which is 2. So just to give you some examples, so if I wanted to take the fourth root of something, another way I could write that is with an exponent of 1/4. So in example A, we have 343 to the 2/3 power. So we could write it like this, 343 squared, but then I take the cubed root of that. We could also write it like this, the cubed root of 343 and square it. The order in which we write the 2 and the 3 doesn't matter, as long as the 3 goes with the root and the 2 is the exponent. If I take the cubed root of 343, that's 7. Because 7 times 7 is 49, times 7 again is 343. And then when I square 7, that gives me 49. So if I wanted to take 343 and raise it to the power of 2/3, we would get 49. Now it says in example B, write 9 to the 5/2 as a radical and simplify. So remember, the denominator is the root. The denominator in the exponent is the root. So I'm going to take the square root of 9 and then raise that to the 5th power. The square root of 9 is 3. So then I'm going to take 3 and raise it to the 5th power. And 3 to the 5th power is 243. So my final answer is 243. Okay, now let's apply rational exponents using our exponent rules. They still follow the same rules. So if I want to multiply 5 times 2x to the 3/4 times 3x to the 1/5, I multiply my numbers together. I have 5 times 2 times 3. That gives me 30. And then when I multiply my x's together, since they're the same base, I have to add my exponents using the product rule. So I have to take 3/4 and add 1/5. So I'm going to make a common denominator. So I'm going to multiply 3/4 on the top and the bottom by 5, so I can get a common denominator of 20. And I'm going to multiply 1/5 on the top and the bottom by 4, so I can have a common denominator of 20. And so when I add them together, I'm going to get 19 over 20. So when I take x to the 3/4 times x to the 1/5, I add the 3/4 and the 1/5, and I get 19/20 for my exponent for x. Okay, in example D, we're going to simplify 16 over 9 to the power of negative 1/2. Now remember, negative exponents means you can clear it and get rid of the negative exponent and make it positive by taking the reciprocal of the base. So I'm going to rewrite this as 9 over 16 to the positive 1/2. And now using my knowledge of rational exponents, I know that 1/2 means to take the square root. Because this number down here in the denominator is my root, and this number in my numerator is the exponent. So I'm going to take the square root of 9 over 16, which is 3/4, and then raise it to the first, which is 3/4. The last example, we're going to simplify y to the 7/2 times the square root of xy by rewriting the square root of xy, because xy is raised to the first power on the inside of the root, and then the root itself is root 2 square root, so that goes in the denominator. Now, I can separate this, the x and the y to the 1/2. When you raise a power to a power, you multiply, and this is x to the first and y to the first on the inside of the parentheses. So I can rewrite this as x to the first raised to the 1/2, which would be x to the 1/2, because I would take the 1 times the 1/2. And I do the same thing with the y to the first raised to the 1/2 would be 1/2. And now I can combine my like bases using the product rule. I have y's here, and I have y to the 7/2 times y to the 1/2. And when I add 7/2 and 1/2, because I'm multiplying like bases, I add my exponents. That gives me 8/2, which is 4. So now I can leave my expression as y to the 4th times x to the 1/2. So this is one way to write my final answer. Or I can actually turn it back into the square root of x, since x to the 1/2 is the same thing as saying the square root of x.